Hello friends, I am Chandan. So this is the second lecture of entropy. So in this lecture we'll try to understand the entropy change for system in case of reversible process. Okay, so the entropy change we know that for in last lecture we just complete this lecture, that is ds for reversible process, that is equal to del q by t for reversible process. This is applicable for reversible process. So here basically this is d and this is del, because this is the property. So entropy is the property, so that is why d is there. Okay, and here q is not the property, so that is why there is a del. Okay, del is there. This is del. Del means this is d and there is a this sign. Okay, so here let's try to understand the entropy change for the system in case of reversible process. So suppose consider this is a reversible heat addition process. So first there is a reversible heat addition process, and if it is a reversible heat addition process, so here consider this is system 1, this is system. Here this is our system, and some heat is transfer from boundary from surrounding to system. Okay, so so if you want to calculate the system's entropy, that is equal to del q by t for reversible process, and as the heat is going into the system, that is positive, so that is why del q that is greater than 0, and t the system temperature that is also greater than 0. So from here you can say that, so we know that this is ds that is equal to del q by t for reversible process. So as q is greater than 0 and t is also 0, so this value will be positive. So this value, so ds value will be positive. Okay, so for system, for this system for reversible so this is a reversible process, as there is a reversible process. So here ds from here ds for system that is greater than 0. Okay, so from here you can say that, so ds that is equal to, you can say that s2 minus s1 that is greater than 0. From here you can say that s2 greater than s1. Okay, the final entropy is greater than initial entropy. That means entropy is increasing. Okay, so this is there. So here that is basically s2 greater than s1. Okay, so here you can say that since system entropy increases by reversible heat addition process. Okay, this is heat addition process, so that is why here you can say that there is a system entropy that is increases, because s2 is greater than s1. s2 that is entropy for state 2, and s1 that is entropy for state 1. So basically entropy is increasing. Okay, this is increasing, the entropy is increasing. So for, you can say that hence system entropy increases by reversible heat transfer process or heat addition process. Now for case 2, this is case 2. If there is a reversible heat rejection process, there is a reversible heat rejection process is there. Okay, this is our system, and in this system the heat is going out from this system, the q amount of heat is going out from the system. Okay, so if there is a q amount of this is a reversible process, suppose consider this is a reversible heat rejection process. So if you want to calculate the ds for system, that is equal to del q by t for reversible process. Okay, so from here del q is going out from the system, so del q is negative, del q less than 0, and t is always greater than. So from here you can say that ds of system that is less than 0, because del q is less than 0, so that is why ds of system that is less than 0. So from here you can say that, so this is s2 minus s1 less than 0. So from here you can say that s2 less than s1. So the final entropy is less than the initial entropy, initial state entropy. So here the entropy basically decreasing. Okay, so here so s2 less than s1. So from a reversible heat rejection process, the basically entropy is decreasing. Okay, So from reversible heat rejection process, the entropy is decreasing. Okay. And suppose next there is a third condition, this if this is a reversible adiabatic process, there is a system, this is our system here, this is our system, and in this system there is no heat transfer is there through the boundary. Okay, so as there is no heat transfer is there, so ds system that is equal to, we know the formula del q by t, as for reversible process, as the heat is not transfer, so here del q that is equal to 0 and t of the system that is greater than 0. Okay, so as it is del q that is equal to 0, from here you can say that this is 0. Okay, as del q that is equal to 0, so from here you can say that ds system that is equal to 0. Okay, so from here you can say that ds system means, from here ds system means h2 minus h1 that is equal to 0. From here you can say that h2 that is equal to h1, that means entropy is not changed, entropy is equal. Okay, entropy is not changed, so here the entropy is not changed. So for a reversible adiabatic process, the entropy is constant. Okay, s is constant is there, s is constant, s is constant, that is entropy not change. So as there is a entropy not change, is the entropy is not changing, so this is an isentropic process. Okay, so that is why reversible adiabatic process is known as isentropic process. So this is very very important. Okay, this is an isentropic process. Why it is isentropic process? For reversible heat addition process, there is no entropy change is there, there is entropy constant. Okay, no entropy change is there, so that is why reversible adiabatic process is known as isentropic process. Okay, so okay, so this is my handwritten notes, you can download it from the description. There is a telegram group, Mechanical Bengali, you can join that telegram group. Like, share, subscribe my YouTube channel. Thank you.